The idea of the BMH algorithm is to find a pattern P in text T. So to do this, we make comparisons between the right-hand letter of the pattern and compare it with the text. So in this example, the pattern is tool and the text is Horspool. Now, the L's align fine, the O's align fine, however, there's a mismatch on the T in tool and the P in Horspool. This then repeats until there is not a match, but still characters are to be read in the text, in which case we use a prefix table to move the pattern along, which will be shown later. If there is a match, then the algorithm returns the position of where the substring starts, and if there is no match and we've reached the end of the text, then the algorithm terminates. First, we need to form a prefix table. This table gives us information about how far to move the pattern along. First, every entry of the prefix table is initialized to the length of the pattern. Next, we initialize the entries of the table, which are in both the pattern and the string, to how far we want to move the pattern along if a mismatch occurs there. Now, this algorithm is very verbose, so I'm going to perform a simple example. In here, the text is simply ABCD and the pattern is BCD. So first, we initialize every entry in the prefix table to the length of the pattern, which in this case is 3. Next, we update the prefix table. Initially, P1 is B, so we update B in the prefix table to 3 minus 1 or 2. P2 is C, so we update the prefix table to 3 minus 2 or 1, and D is still 3. So now that we have the prefix table, how do we search through the text? First position is set to 0. While there is still string to search through, we set J to the length of the pattern. While the letters in the pattern match the letters in the string, decrease J. If J is equal to 0, then the pattern is in the text, and so we have found it. Else, we increase the position based on the prefix table. Now, this is very verbose code, so an example proves this really nicely, so if you're feeling lost, don't worry about it. Here's an example of the Boyer-Moore-Horspool algorithm at work. So the text is my name is Josh, and the pattern is just simply Josh. First we form the prefix table, and note that I've used exclamation marks to simply make it easier to break up the sentence because visually it's hard to tell where a space is. First, the mismatch character is at n, so we consult the prefix table for n and move 4 places to the right. Next, we mismatch on an exclamation point. Consult the prefix table and move 4 places to the right. Now, we mismatch on J, however J is in the pattern. So we consult the prefix table and move 3 places to the right. The strings are equal, so we've succeeded. So one really interesting application for string matching is in the field of bioinformatics. One example within this field is genetic sequencing, where tests can be done to check if a person has a particular disease. For example, cystic fibrosis is caused by a malfunctioning protein on chromosome 7. But chromosome 7 is simply 159 million letters, and if the string for cystic fibrosis is not present on chromosome 7, this person is likely to suffer from the disease. We can use string matching with the letters for chromosome 7 as our text and the letters for cystic fibrosis as our pattern. The Boyer-Moore-Horspool algorithm can be easily extended to search databases and other large volumes of data quickly and easily. A recent example of this is the leak of Snapchat accounts and phone numbers to the internet. People wanted to know if their account data had been released, so a website was created to allow users to check if their data had been compromised. This type of problem lends itself quite well to the BMH algorithm, as a user could input their username to check if their account. The worst case for time complexity is big O of length of pattern multiplied by the length of the text, which could lead to a huge amount of comparisons. For the aforementioned examples, searching to see if my Snapchat username was in a published database would take under 37 million comparisons, while searching to see if someone has cystic fibrosis could take under 30 trillion. However, the best case gives us big O of length of the text divided by the length of the pattern. For calculating the prefix table, it would take big O of the length of the pattern plus the size of the alphabet, which could take a large amount of memory and time for larger alphabets.